Thank you very much for the department. I really very honored to be invited here, and I thank also the Department of Chemistry, NYU Abu Dhabi as well for the kind invitation. And if I can find. So my talk today will be split into two halves, actually. These are, sorry for the little typo in my abstract. There is an extra S that I removed. But I will show you a few of the things that I'm interested in exploring, especially more lately. And they have to do with the field effects on reaction and reactivity. So before going into the business, let me show you where the work is done. This is Mount St. Vincent University. It's a small university, undergraduate primarily, in Halifax, Nova Scotia. And this is Dalhousie University. I'm affiliated in both. This university is primarily undergraduate, as I said, so this is where I get my brilliant undergraduate students. And when I want to have access to graduate students, it's mainly through Dalhousie, and these are two mirror images in time. Reflection in time. So, where is Halifax? It's there. It's a little bit here on the upstairs to the left, to the right. And it's a beautiful city. If you haven't visited Nova Scotia, I really take this opportunity for a small commercial that you should visit. And if you like seafood, well, you know, you should be, you should feel welcome, and you will be really, really treated with good lobster. So this is my friend and collaborator, Renato Bensasson, from the Musée de l'Histoire Naturelle in Paris. And this is my graduate student, Shaheen. You will see a better picture of him in the acknowledgement section, where he was helping Renato eat his lobster. So the outline here, I'm going to talk about two parts. So it's basically like two small talks. One part will be the effect of intense field on this reaction, and the other one will be the intense of strong field on this reaction, which is double proton transfer reaction, which is a model for the Lovedean mechanism of mutation, very simplified, but you know, we just want to learn some principle. The first reaction here, the goal is, or the focus is the control of the reaction. The second part, the goal of the study is to uncover what happens in situ, in a crystal, in the cell, in a reactive, in an enzyme active site, and so forth. So let me start with the first part. So we're interested in this reaction of methane with halogen. And the halogen that we're going to look at are two, fluorine and chlorine. And just to get you a little bit of the context, and I'm not going to describe this in detail here, but this is the groundwork, the fundamental papers were published in between 1904 and 1906 by this group of Jim Wright, Ivanov, and Matusek in Carleton University in Ottawa. They started by looking at this very simple system, the hydrogen abstraction, the exchange reaction. You have a hydrogen molecule and a hydrogen atom coming in. The hydrogen abstracts one of the hydrogens, and you have a hydrogen leaving and a hydrogen atom remaining on the other side, right? So that's the simple reaction they looked at, and I'm not going to describe the work here in detail, but they are the first to note that you can actually control this type of reaction by an external laser field. And they were among the pioneers also to describe, or even perhaps even, I'm not sure if they coined the term, but I think they might have coined the term of polarizability and dipole moment surface. I'm just going to present it now for the record, and then move on. So this is the polarizability surface. It looks like a potential energy surface, but you have here one of the distances between the two of the hydrogens. This is the distance between the two other hydrogens. So you have, you know, a two-dimensional plane here. And what is plotted in the third dimension is not the energy in this case, but rather the polarizability of the entire system, the reacting system. And you can see that there are valleys and things. Looks like an energy surface, but it's not. And of course, the contours here give you the value of the polarizability. I think it's an atomic unit. This is, for instance, if you plot the profile, the reaction profile, if you have, unfortunately I do not have the energy surface that goes with that, but you can imagine something similar. So you have these valleys here and the valley there, and you have the minimum reaction path that links them through the transition state, and then you flatten this out on a piece of paper and you get this. So this is the potential energy curve that describes this system. And you can see here that with interaction with the field, the height of the barrier is significantly reduced. You can even have here a little bit of a bound state here, near the point where the transition state happens. I am not describing this very well, I know, but it will become apparent when I get to the part I will describe in detail. I'm just showing you that there is something called polarizability surface and dipole moment surface. That's the purpose of these slides. I'm not describing it in detail yet. This is an example of the dipole moment surface. And of course, the polarizability surface, here is the concept that I want to make very clear, especially for if there are students in the crowd, that the polarizability has dimensions of volume and therefore is always positive, it cannot be negative. However, the dipole moment is a vector, so it could be either positive or negative. And if you look here, this is the reaction path, the minimum energy path here, plotted on the dipole moment surface of the system. And if you now plot, instead of plotting the reaction profile, you plot the dipole moment profile. In other words, the dipole moment along with the reaction. So this is the reaction, this is the minimum energy path. If I plot now, instead of plotting the minimum energy path, I'm plotting the value of the dipole moment at every point, and I get this curve. And you can see you get from a negative, of course it's a symmetric system, right? The hydrogen, you have H2 and H. That picks up an H, it becomes H2, and leaving an H, so it's a symmetric system. And of course, the dipole moment will flip to the other side. This is why you have a big peak right before the transition state. And in this case, at the transition state, you have a zero dipole moment, which is here. And the other side is the mirror image. Of course, the direction of the dipole moment, in this case, depends on your definition of the coordinate system. You will see later that that this is not that you. I'll get to this point again. Just keep this in mind. That, of course, the direction of the dipole moment, if it's negative or positive, depends on how you define the coordinate system. Right? If it's aligned with it, it's positive. If it's anti-aligned with it, it's negative. So, first of all, this is the reaction we're going to study. And actually, we're not going to study. And the reason is, that's good if it is in vacuum. In absence of external field, you can have any orientation of the system. But in presence of an external field, the field actually orients the reactants in such a way that that reaction becomes almost irrelevant in intense laser field. This is the kind of reaction that you will have. The external field orients it. For example, to give you a small example, a field with 10 to the 13 watts per centimeter square would even a molecule with no permanent dipole moment, such as chlorine or iodine, will orient at 10K within 20 angles, 20 degrees angle. The thermal smearing is not that big at all. So this is a very relevant system when you are in a very intense laser field regime like this. So the second thing, so I'm just bringing you into the calculation, trying to show you what are the assumptions, what is the model we're studying, and you'll see at the end how this all fit together. I know it's a little bit disconnected at this point. So here I'm looking at the collinear attack here of the halogen and the methane to get the HF or HCl and the methyl radical. The next thing, how I'm going to orient the field. The laser field, first of all, the field, we are going to look at plane polarized pulses of two-color laser fields. So these are wave packets, and they are plane polarized. So they have a preferential plane in which the electric and the magnetic field oscillate, right? How am I going to orient the field with this? Well, in order to affect this reaction, the field better be along the line of approach. So it better oscillates this way. So the laser pulse is going to come this way, right? But you can orient it at any angle. It could be like, you can imagine it can come this way, it would be less efficient, it can be this way, it would be not efficient, and so on. So there is a parameter here, theta. And we're going to make theta 0. It's an in-principle study here. We try, so I'm orienting the field. The field is parallel to the z-axis. Or anti-parallel, doesn't matter, but you know, oriented with the z-axis, plus or minus. So these are some technical details here. One, we chose these two reactions because one is exothermic, the other is endothermic. The rest is technical detail. I don't want to spend too much time on that. I want the concepts here. The tunnel, first, before we're putting these molecules in very, very intense laser fields with frequencies far below the frequency required to excite. So we're living in the ground state. We're not going to excited states. The frequency is not, there is no photon absorption. When you put a molecule like this, or an atom, say the simplest thing is put an atom in a strong external field. What an external field is, it's a ramp of potential. So if you add the nuclear potential, so this is the potential due to the nucleus, you add this thing, and you look what you get. You get a distorted potential, and from elementary quantum mechanics, you know that something like this is a barrier, and if you have an electron trapped in there, it can leak out of the barrier through the process of tunneling. And note as well that you're talking about oscillating time-dependent fields, and therefore, you know, that can change, you know, the direction of the ramp can change, and you can have the tunneling happens sometimes to the right and sometimes to the left under the influence of this field. All right? So before going there, we want to ensure that not a lot of ionization happens in the lifetime of the laser pulse. Otherwise, you wouldn't be studied the system you set out to study, right? So there is the famous, equation for tunneling ionization that you can find in Landau and Lifshitz or any standard book, whereby the rate of tunneling ionization given by this W, or omega, is basically dependent on two things. This field strength, which appears in the exponential here downstairs, and the ionization potential of the molecule. These are the two variables. And this is an approximation, but it works very well in a lot of cases. So first of all, and before going into the study, I want to make sure that the field intensity we are using is not ionizing my system. And this is the next thing. The way to do that is to avoid ionization. You use times of the pulses that are shorter than the shortest characteristic time of an ionization event. So the system doesn't have time to ionize during the pulse. That's the basic idea I'm trying to transmit. And to show you how short of a pulse you can reach, and this example is not entirely relevant to my talk, but it's relevant to the area of my talk, is the pioneering work by Professor Cheng in Florida, whereby he was able to, I think he holds the world record of shortness of pulses. He has, I think he reached 70 attoseconds of pulse. And in order to do that, you don't have, in order to get a pulse like this, you cannot do an IR pulse like this. So you don't have enough oscillation in this short amount of time. So you have to go to high X-rays. And that's not what we're using, because that will excite the system. It will even knock electrons out of the system. So, but I'm telling you that you can, what I'm trying to tell you is you have a tremendous amount of control on the duration of the pulse, up to this. We are in IR mode, though. We're far from the attosecond regime, right? We're in the femtosecond. These are the tunneling ionization versus the intensity. So here we have, these are the intensities. We selected these two intensities on the basis of previous work by Ivanov and others, that they are reasonable, and we find that indeed, with these intensities, you can have experimental pulses that are short enough not to let the system ionize, but this is my threshold. I can't go beyond that because here you're already borderline here. All right? Any questions, by the way? Please feel free to interrupt. For a molecule in an external field, you can expand the dipole under the field in this manner. And from previous work that I'm not going to show, and you can actually, there are numerical examples, there are numerical calculations that shows that all these higher terms are contributing almost nothing. It's a small correction. It's almost 10 to the fourth. This term is roughly 10 to the fourth as important as this one. And beyond this intensity of radiation, this approximation fails anyway. So for our purposes, the first two terms are enough. And what they mean is mu is the dipole moment under the field, the mu zero is the dipole moment without the field, epsilon here is the polarizability, alpha is the polarizability, epsilon is the field strength, right? So if you set up a Hamiltonian, in order to get an energy from a dipole, you have to multiply by E, the field strength. So here the E becomes squared, but your E here is time dependent. So you're writing it as E function t, because it's a wave now, it's not just E. And the square here comes because you had an extra E in order to get an energy. And notice the cosine theta here. Cosine theta is just this angle at the beginning that I said we're going to set to 0. In other words, the field and the reacting system are aligned, so your cos theta goes. Right? If you actually put the functional form that describes a wave, which is the amplitude cosine omega t plus an initial phase factor, right? And that's to be defined later. And I will show you how experimentally you can actually play with this in order to modulate your potential energy surface. So you obtain the result. If you plug in this here, so you plug in, I'm sorry, there is a little bit of math here, but if you plug that here, square it, and then use this identity, I should have had these reversed actually. I don't know why I did it this way, but anyway, you got the idea. Plug this upstairs, use the identity, you get that result. All right? What I missed to tell you, I just neglected that term, the perpendicular component of polarizability, because it's the sign's 0 anyway, and even if it's not exactly 0, even if it's within this 20 degrees, is very negligible. Take it from me now, I will show you later that it is, by calculation, that this term, even if it's not aligned 100%, is negligible. So that's the Hamiltonian that we get. Now, here is the interesting part. This is just some simple manipulations here. You know, you take that into common factor, so you have to divide by this. Of course, this is dimensionless. If you work out the dimension, that's just a number. And notice inside here, I have cosine omega t plus phi And here I have cosine omega twice the frequency plus twice the initial phase. When you add waves like this, what matters is the relative phase. So you can drop one of these and drop that, and that becomes 1, and you reduce this to this. That's striking, because this is exactly the functional form that describes a two-color laser pulse that has exactly this functional form. We have here f, which is a constant, dimensionless, which basically is that. So you have that. And this is the frequency-independent Stark shift. So this is how your potential energy surface completely vary, because the polarizability varies. So the entire ground state potential energy surface modified depending on how the polarizability changed, the polarizability surface that I presented at the beginning, right? So now, before getting here, let me tell you a little bit about the experimental side of things, because otherwise it's just fiction, right? So this is an experimental setup. I hope you don't pin me down too much on the details here, because I'm not an experimentalist. But here's what I understand from this. This is an experiment by Paulus, who is a pioneer in the field. And you have actually here two spectrometers that measure the distribution of momentum, the momentum spectrum of the ejected electrons. And I alluded, I'll step back one step. The reason I'm showing you this slide is to show you that you can actually control this initial phase phi that I had in the equation experimentally in the lab. That's why I'm showing you this. How is this done is this, and the next slide. Here is how it is done. You have two spectrometers here. This is in ultra high vacuum. You inject xenon or some rare gas atoms from the top, and you have a laser beam coming in here. Forget about this for a second. You have a two-color laser, so it's a superposition of two waves, basically. One is usually twice the frequency of the other, so you have these wave packets, these pulses. And you adjust the optics of the equipment so that the focus of the laser is right here where the beam comes in. And then you have two slits here that select those electrons that go into the photoelectron measuring device. So what you're measuring here and here is the distribution of momentum versus counts. So how many electrons have how much momentum? Kinetic energy, inverted quotations. Versus what? Versus phase-stabilized wave laser pulses. Phase-stabilized laser pulses. So how do I stabilize the phase in the laser pulse? What does it mean to stabilize the laser pulse? If I have a pulse, it usually has a Gaussian shape like this. This is the superposition of several waves, right? Now I try to draw two that are similar, and I'm going to try to make the difference clear to you about what I mean by that. Here's one possibility. Here is another one. And you can imagine all sorts of different ones. Look here, I have a maximum with the maximum of the Gaussian envelope. Here the maximum is downstairs with the Gaussian envelope. So how does the carrier wave maxima match with the Gaussian envelope maxima? That's what I wanted to show, the group versus the individual carrier wave. So by using glass thickness, glass thickness can slow down light because it's a refractive material. I'm sorry, I'm going very pedagogical here because I see people who might be students. So the glass thickness slows down the carrier wave but has no effect on the Gaussian envelope. So by controlling the thickness of the glass, you can actually shift the carrier envelope inside your Gaussian packet. So here you have a brilliant thing. You have two very thin triangular prisms that can be slid by in order to control the thickness. And when you do that, here is what Paulus and coworkers have observed. This is the thickness of the glass in micrometers, the delta X here. This is the shape of the Gaussian pulse that was sent into the focus of the laser. You can see here that the Gaussian, if you draw a Gaussian here, this matches the Gaussian maximum. This one is not at the Gaussian maximum. Actually, there is zero at this point is where the maximum is here. You see the point. I think you get the point now, right? It's clear. You can modify the shape of the pulse. And look the result that you get. Look at the difference between the right and the left photoelectron spectrum. When you don't have the phase stabilized spectrum, you get this. They top of each other. When you have the phase stabilized spectra, you have different distribution of momentum between the electrons to the right and the electrons to the left. And this is where you get this splitting, right? So this is the equation that describes this laser pulse, and this is the equation in the Hamiltonian that we have. And I just showed you that you can control that experimentally. So for instance, when phi is 0, to maximize this, the cosine omega t corresponds to the maximum of the Gaussian envelope. Why? Because when phi is 0, that's gone. You're adding two cosine things, they reinforce each other. But if phi is pi over 2, the cosine becomes sine, it cancels. So you have a 0. It's complete destructive interference. So, etc. So it is possible, in other words, the short method, take-home method, you can control phi that appears in this equation experimentally with a pair of glass prisms. So if you go at a very high frequencies, not enough to excite to the excited state, but still high, then the cosine terms average to 0, of course, and you're only left with the Stark shift term, which is always stabilizing the Stark shift term because it comes with a negative, and that thing can only be positive, so it's always stabilizing. No matter what shape polarizability surface you always have stabilization. So the trouble comes from the other two, from this one, because the mu here could be positive or negative, as I explained. And of course, that's dependent on the way you choose your coordinate system. But if you reverse your choice, you reverse the phase. So the physics is the same, right? Doesn't depend on your... so here, at the limit of low frequency, this is the other limit, the Stark effect is maximized when? Well, when omega t is 0. So why not choosing this as a classical test case? Because we have in an Avogadro number of xenon atoms, I have every possibility. The wave will hit the xenon atom at any, or in case the reacting system in our case, at any phase. So let's pick the extreme case, because some of them will be hit at the extreme case anyway, or close by. So the extreme case is omega t is equal to 0. That's what I'm going to pick. This is a choice I'm making. It's a special case, but it's significant and meaningful special case. So that's what you're left with. You're left with an equation whereby you have the phase, the intensity of the field. I don't know if I'm going to have time to do the second part, but the intensity of the field, the dipole moment, the polarizability surface. Sorry, I forgot to say, this is the parameter that describes your position on the reaction path. So this is your reaction coordinate, if you like. So Here is the potential energy surface of the system with fluorine. And it has a small barrier here of 4.6, right? And let's look at, just I want you to remember this for the purpose of the next discussion. Here is the dipole moment surface of the same system, and you can see here that we have a huge negative peak near but not exactly at the transition stage. Slightly, it's a late peak after the transition state a little bit. I'm sorry, this is a reminder for me. I mean, because I can never remember these. Which one is zero, which one is never. So it's not for you, it's for me. So here I have, let's pick a phi choice of 0. So cosine 0 is 1. So plug in 1 here, plug in 1 there, and you have a destructive interference. Why? Because the mu is negative. So negative and negative is a plus. This comes with a negative sign, destructive interference. If you pick pi as your phi, then this is negative, negative plus, negative becomes negative, so negative and negative, maximizing the stabilization. So now let's play with this a little bit and have fun with it. So here is the polarizability surface. You notice there is a huge peak here. This is the ZZ component, so along the reactive line. And I told you at the beginning, and I keep my promise, I told you that I'm going to show you that this term, even if the theta is not 0, is unimportant. And here is where it comes. Because this is one of the other elements of the diagonal elements of the polarizability tensor, the XX or the YY. Look, it has a small, not negative, it's all positive, but it has a small peak here, and look at the magnitude, it is just 1 atomic unit versus 50. So it's really negligible. You see here the difference is 20 to 70. Here is what? 1.64 to 1.78, or 17.8, sorry. So it's really negligible, even if the system is not completely aligned. So it's safe to neglect that term. That's what I'm trying to say, because not all systems are going to be exactly aligned with the laser. So here is the other one, the other guy, the chlorine, 9.3 barrier, forward barrier. This is its dipole moment surface coinciding the peak with the transition state. Here is the polarizability, the main one along the reaction approach. And here's, I didn't even bother to put the YY because or the XX because it's so weak, I didn't even bother. And that's a good point to put that result. And this is really significant because here, look, I have, these are the intensity. So in all these plots, the intensity is the lower intensity, the intensity of the 10 to the 13 watts per centimeter squared. At that intensity of the laser field, the dark is the field-free potential energy surface, the one that I showed at the beginning, the PES field-free without lasers, the dark one. This one is the dipole contribution only, that second term contribution only. And this one is the third term, which is the polarizability contribution only. Now add them up, and you get that. Because of course, in this case, at that, with phi equal to 0, I forgot to mention, this is very important. The phase here is 0. With this phase, with this intensity, when you translate it into field magnitude, you get these results, and you add this plus that, you get this one. Of course, because it's still up, but less up than this, because this one goes down. So this is the result, right? So this is, with the two contribution, you have an enhanced barrier. So you slow down the reaction with that choice of phase stabilized pulse and intensity. However, and that's given that phi is equal to 0. If you switch the phi and make it, move the glass a little bit around, make it phi equals to pi, then instead of having a raised barrier you can actually have a lower barrier. Actually, no barrier, the reaction. Now, in the other side, you can now, this is exactly the same, but for chlorine. And for chlorine, look what happens. Instead, this is the, without a field, the naked barrier, the naked potential energy surface. This one is the sum of the two components. You know, this is the dipole, this is the polarizability component. Sum them up, you get that. A high barrier when you have the phase stabilized at 0 degrees. And if the phase is 180 degrees, now you have what? A bound state instead of what? A transition state. A bound state instead of a transition state. I think this is phenomenal. I mean, of course, you're going to grill me with questions about that, but you know, let's talk about it. So here, this is the next intensity, 3 times 10 to the 13, and the effect is even more marked. You see, it just goes zip into product. There's not even a hint of a barrier. And this is the result for the chlorine one. A significant bound state that could accommodate perhaps 1 or 2 vibrational leveling. So that, well, I'm not as interesting as this is. I'm going to skip it because of the time, but basically this is a way to partition the molecular dipole into atomic component. I'm not going to go into this detail, and we don't have time now. But I basically, the result of this work that was done by Shaheen, the graduate student that I didn't show the picture of yet, is to show that the jump in the dipole moment is because of a charge transfer term, not because of an atomic polarization. So in other words, the atoms, there is this peak, huge peak in the dipole moment, not because the shape of the atom changes, but rather because there is a transfer jump of electron from one atom to another. That's basically the bottom line here, but I'm not going to go into too much detail. I end that part by a quote from someone who I really admire, Professor John Polanyi at University of Toronto, and it really summarizes that part. He says, in closing, I mentioned 2 further approaches. This is closing of his Nobel lecture in '86. In closing, I mentioned 2 further approaches which could assist materially in the quest for understanding of the choreography of chemical reactions. In the first, attempts are being made to observe the molecular partners on the stage. And the second is to have a hand in writing the script according to which the dynamics occur. And he closes his lecture by these very inspiring words. This is my emphasis. Any question about this part before I quickly rush through the second part? Okay, the second part, yeah, we can discuss it later, but you know, we can, let me rush now through this part in the little bit of time that I have, probably 10 minutes, right? Right. Pardon me? 20 minutes? Really? So, intense electric field effects in the natural microenvironment of the cell. And this is a study that was done with my student Alia Arabi, who started as an undergraduate and published as an undergraduate, and then moved on and did her PhD, co-supervised with Professor Axel Becke at the University of Toronto and myself. But her thesis was partitioned between Professor Becke's and mine, and this was part of my, the part that I supervised. So why are we interested in this in the first place? Well, as you know, many experts in this audience know very well, very intense electric field exists in the cellular environment. I mean, all what it takes is look at a picture like this. I don't even know what is this. I don't remember where I got this from. But look at this. You have magnesiums, lysines, you have histidines, glutamic acids. I don't even know what is this, know what it does, but the point is clear. Very strong fields are ubiquitous in the biological system, and so here, you know, you can pick any example you want, but that's not all. Back of an envelope calculation, I love these because they're easy. back of an envelope calculation, you have, you know, what? In an enzyme pocket, you have plus 5 charge atomic units, minus 5 charge atomic units. In the middle, if you have the distance of 10 angstrom, look at the field that you have, 10 to the 9. If the distance is pushed to 30 angstrom or 35 angstrom, it becomes more like 10 to the 8 volts per meter. Very, very intense field. You can actually, in an X-ray diffraction experiment, apply experimentally fields up to, and the limitation is practical, and you can apply fields up to 10 to the 7. They are not strong enough to make huge dramatic changes in the diffraction pattern, but Chérif has done the theoretical work whereby he described the theory of the Fourier diffraction pattern, you know, the Fourier transform of the perturbation induced by this weak field, because 10 to the 7 compared to the nuclear field is very weak. It's like 10 to the 4 times weaker than the typical field you encounter inside the molecule. So this is, for example, here, to give you a sense of it, this is again an experiment whereby you fly these, from this nozzle, you fly mist of methanol in between plates here, and the field between the plates is typically the 10 to the 6 volts per meter, and the methanol droplets expand like this and start to eject ionized methanols from the sides. But that kind of, the field that does this is about 10 to the 6 volts per meter. I'm just trying to give you a sense of the strength of the field and how it relates to your bench experiment. This is something also that a lot of very great experts in this audience know. They have a complete sense of the kind of field in an STM is about 10 to the 9 volts per meter. So these fields are ubiquitous all over the place. There are even papers that describe field in the normal molecular, not even ionic, molecular crystals. Again, within 10 to the 8 volts per meter is commonplace. So here is the calculation. This is the initial idea was sparked by something that turned out to be very naive. I was working at the, I was volunteering in something called the Ontario Public Health Association, and I was just out of interest in the environment and so forth. So came up to me the task of reviewing what is known and what is not known about the health effect of cell phones and, you know, stray fields that we're exposed to. And I'll say why it's naive, because the cell phone field is like 10 to the 12 times less than this. So, you know, when I have the cell phone here, the damage apparently happens from the heating, not from the vibration of the wires and stuff, right? It has nothing to do with the electric fields. It doesn't have any effect on the barrier or anything like that. It's too weak. But that was what initiated the thought process. Then I thought about the business of the Lovedean mechanism, something I read about when I was much younger, and, you know, I find it fascinating that, you know, one of the possible mechanisms of mutation and cancer and, you know, giving the palette for even things like evolution to pick from, you know, the natural selection to pick from, is the quantum jumps that can happen in the DNA dimers, randomly, and give you the mutations and the process of aging and damaging the genetic code by this. The Lovedean mechanism is very well known. So that was a little bit, you don't write this kind of thing in a scientific paper, so this is a good place to say it. What led to the thinking about this. Now that in the scientific paper, the following has happened. So we studied these field intensities from 10 to the 8 to 10 to the 9 volts per meter for good reasons. And here is what we get. Just to give you a hint, and just to link it with my first talk, or my first, you know, half talk. Of course, this is from standard electromagnetic theory. If you have, this is the field strength squared, is related to the intensity of the irradiance of the radiation you're talking about, with speed of light and the field and the. Here, I'm sorry, I'm mixing the symbol. Epsilon 0 here is the permittivity of free space. E is the field strength. I know it's. I'm changing the symbols here, but I should have kept the symbols consistent. So anyway, that how you relate one to the other, and to give you a sense, the other work whereby you have this irradiance is far, far more than what you have here. Like here, if you translate this into irradiance, there's several order of magnitude less irradiance than that. If that was a field of a laser radiation. I forgot to mention something, by the way. In the laser business, I don't know if you notice I didn't speak about the magnetic field at all. And it's an electromagnetic wave, but we ignore the magnetic field because the magnetic interaction is really, really weak because of the form of the Lorentz equation. There's a C downstairs, so if the velocities are very small with respect to light, it's a negligible term. So we don't look at the magnetic field, we look at the electric field. So the tunneling ionization, of course, is negligible here because it's a very weak field compared to the previous one, or if the previous one already was negligible, so here's, believe me, you don't even need to look at these numbers. Here, this is just standard transition state theory, the rate constant, and this is the standard transition states theory, and this is a correction due to quantum mechanical tunneling. The simplest one is the Wigner one, whereby this is the magnitude of the imaginary frequency, and by plugging in all these numbers, here is what the field does to the double proton transfer reaction in formic acid diamond. It lowers the barrier significantly, so this is the field intensity or field strength. This is the delta G dagger. You see, whether all level of theory give consistent picture but very different result, and therefore have a small tiny error here or a small tiny inconsistency in the results here can have an immense repercussion on the actual rate constant, right? But the qualitative picture that emerged is very, very consistent. Look at this, they are almost parallel. I mean, quantitatively, we're talking like day and night here. 1 calorie here is huge, right? 1 kcal per mole is huge here. But they are, it's very consistent. So this is the parallel field, the field that is parallel to the reaction, and these are the ones that are perpendicular in the two planes. So you can see that the barrier decreases significantly with the field strength, but also does the frequency, the imaginary frequency, which means that the surface at that point is flatter. So in other words, if you look at this, the field suppresses the barrier and flattens it. So it does two conflicting effects. When you flatten the barrier, you slow the tunneling. So you slow the reaction. When you reduce the barrier, you increase the over the barrier kinetics. So it's conflicting. The net result is still acceleration. This is the K of the reaction corrected with the tunneling, or you can convert it to T half, but here the K in DFT or in EZ, notice that there is 1 order of magnitude difference here because of this 1 kcal per mole difference in the level of theory. See how important is the level of theory? Because we tend to be blasé, we computational chemistry. This is a self-inflicted criticism. We computational chemistry, we say, oh, 1 kcal per mole doesn't know. 1 kcal per mole is like 10 order of magnitude in K, right? So, effectively, oops, I get too excited, sorry. So, effectively, both of these can be fit very well to an exponential relationship. Look at the R. You know, very, very close to an exponential fit. Perfect. The take-home message here is that if it is exponential, then a small tiny change will be magnified. A small tiny change in the field will be immensely magnified in terms of K. That's the take-home message. People here in this great institution have done pioneering work in QMMM. And that's great, because this is the way to implement or to include field effects in their, almost directly in the calculation. You know? So that, you know, these observations are completely consistent with the philosophy of QMMM and you know, this kind of mixed quantum classical approaches. I do not have time to go to this really exciting work at this point, but I will, because I don't want to miss. This is she actually did the work on the DNA base pairs, and the conclusions are similar. You have a 4-fold or 5-fold acceleration at these kind of fields that you encounter in the cell. And before I close, I have to thank the people that contributed to the work. I mean, Professor André Benrop, he's the pioneer in this field, and if I know anything a little about this field, it's due to him. And these guys have done the work. Alia was my undergrad student, and then she became my PhD student, and she just graduated in August. And Shaheen is the guy that was doing the part that I skipped quickly about the origin of the dipole enhancement near the transition state. And he's the one that was helping my great friend René Bensasson eating his lobster. Thank you very much. And of course I have to thank these guys. Thank you. Is there any questions? Mike?
So just addressing the issue of relevance and
Right.
with respect to the strength of the electric fields and comparison to biology.
Right.
How similar are they?
Pardon me,
How similar are the fields that you would experience in a laser, right, compared with biology, where you have
The
dielectric
fields,
and you have a lot of other things.
Great question, thank you. Here the fields are very idealized. We're trying to understand the principles. In biology, as the picture I've shown you, the field would be very complicated. If I plot an electrostatic potential of these enzyme pocket, it will be all over the place. You have to take the gradient of that minus to get the electric fields. It will be all over the place. But the kind of strength, that's what I was trying to get. For example, a DNA base pair is sitting there. There are phosphates, there are sodium, perhaps calcium, perhaps potassium ions around. There are maybe platinum ions in a drug or something, you know. There are very strong fields. I haven't gone into these details, but this is very idealized. This is just in principle kind of study to get a feel of how these fields influence the speed of the reaction. I'm not sure if I answered the question completely, or
I'm just wondering because you
You're
have a lot of possibilities for screening the field, which you don't have in your laser experiments.
Oh, the laser has not much to do with the biology. The laser is more in the field of coherent control, in terms of influencing reactions by outside influence. So that's the laser part. So it wasn't very related to the biology, but the next part, which was intended to look at the very basic model of the Loveday mechanism, is very idealized. I realize it. It's very idealized. But it's the first step. There is much room for improvement and much room for additions, right? Yeah. Okay. Mark?
So coming to the Loveday mechanism that you talked about, of course, you know that the difference between the formic acid dimer and the real base pairs is the reaction
Enormous.
is highly asymmetric, right?
Yeah.
And you look at these profiles that you would plot, and of course, it's significantly uphill to form these rare monomers.
Right.
Now, in the presence of the field, you would expect the barrier to come down, but what matters is actually the reverse reaction.
Right.
And we suggested a couple of years ago that the quantum effects actually lower, almost obliterate the barrier to the reverse reaction when there's no field there. Presumably the same thing would happen in the case of the field. But in no field, this is why you never see rare monomers form, right? It's spontaneous because of that. Can you
It's
comment
an
on
excellent
that?
question. I mean, yeah, it's a great question. Thank you for asking that. I mean, oops, Control N. Where is it? Here, you're right. I mean, there is. You see, there are 9 ways of. For example, in this guanine cytosine base pair, you can have these guys going opposite. You can have these guys that I forgot how many ways, but there are, you can get these going, or these going, and you can have the field this way, and you can have the field this way, and you have the forward reaction, and you have the backwards reaction. So it's a combinatorial explosion problem. She has it, yeah, we've looked at these. I cannot remember exactly what was the situation of the backward, but I can look it up. I mean, I would be very happy to discuss it further, perhaps by email or in person, you know, or perhaps finding something, a thread in common, you know, if you're interested.
So you talk about first part, you find the kind of field have the strong effects on the transition barrier, and you say that you did a partition. What's the take-home message? Can you summarize that?
Yeah, the take-home message is that, you see, we can break the, yeah, see, this is the density control plot, and it's broken down by the Bader's atoms in molecular theory. So these are the zero flux surfaces in the gradient vector field of the electron density.
Yeah.
And they are sort of like quantum subsystems,
Yeah.
whereby the kinetic energy, at least two definitions of the kinetic energy density, when you integrate it, you get the same number.
Yes, yes.
So they have desirable quantum properties, these subsystems.
Mhm.
And you can you have dressed properties, you can dressed densities that you can integrate over this volume of the basin and
Yeah.
get numbers. So we get the charges, we get the dipolar polarization. I don't dare saying dipole moment because most of them have charges and therefore it's not uniquely defined.
Okay.
But you take the nucleus as the center, as by, you know, you have to pick an origin in this case because it's origin dependent. And in doing so, you have you can break down the system, in this case it's not molecular, this is the whole system dipole moments. You can break it down into two contributions that sum vectorial. You can have a charge transfer between basins, which is in this one. This is the total. This is the total atomic. So this is the contribution of the fluorine to the total atomic, to the total. This is the total. This is the system. So this is this one. It's the system dipole moment, but this is at the transition state. This is this part, right? This, sorry, not at the peak. The peak happened at 0.4 here. So that point corresponds to this arrow. And this thingy, this little thing here, is due to the polarization of the atom, the distortion from sphericity of the atom is very, very minimal. The major thing is from the flow of charge between the atoms.
So basically, the electric field will kind of facilitate the electron transfer by the
Exactly.
reacting.
Exactly. There you go.
So in the first part of your talk, you showed a number of profiles
Right.
showing polarizability as a function of the reaction.
Right. Yes.
And one of them had like a bound state, at the
Yeah.
transition state. I don't quite, is there any experimental manifestation of that phenomenon? Is it just predicted, or what is it?
There is, first of all, I can't answer your question completely because I'm not aware of all the literature out there because I'm relatively new in this area. So I'm still learning.
So you predicted that there would be
But-
a bound state?
Yeah, but people like Paul Corkum at NRC has done stuff like that, you know, I can't answer you 100%. I'm not sure if it has been observed, but there is a high likelihood that it has been done, and if it has been done, it's perhaps by Paul Corkum, and there is another person in MIT that I cannot remember the name right now that collaborates with one of my collaborators that also does this kind of experiments. I can give you the name by email of these people.
How about the rest of the curves that you showed, plots, the profiles? Is there any correlation with experiments?
Not yet. It's so far we're hoping that the experiment will corroborate it. But we see it's an in principle study so far. So
Also, in
We're
the
learning.
electric field, in the
Yeah.
electric field experiments, you have a polarized light wave, but you have random orientations of the reactants. So how you take that into account? You might get different results as a function of orientation of the reacting in the transition state.
yeah.
So the electric field
The
is
field-
defined, but the orientation of the transition state is not.
the orientation of the
Well, it
transition.
could be, I mean, the interacting species could have random orientation with respect to the electric field.
But the field orients them. The field, you know, it favors the parallel orientation. It favors it. The dipole likes to be opposite to the field if you take the physicist convention, right? So it likes-
What's the energy relative to KT or RT?
Yeah, that's a good question. The energy, the field, yeah, that's a good question. I don't have the answer to you right away. But it's the back of an envelope. We can get you this. You're right. I should have looked at that. What's the KT? But you see, yeah. Here, for instance, these guys align at this field intensity at 10K within 20 degrees. And these do not even have a dipole. But you're right, I should have looked at that. You're right.
So it's a low temperature.
I have to get you that number. Yeah. Look at the temperature will make them.
Any other questions from the audience? Okay, well, if not, then I thank you very much.
Well, thank you very much.